So here's how we create the heaped int tree and insert the nodes for our binary search tree. You'll see the overall structure for creating the heaped binary search tree is very similar to what you've done already. There really isn't any big changes to that. And then inserting the items, frankly, there isn't much difference either. Just remember that we're using the arrow since we are using a heaped variable instead of a static one that would be replaced with a dot. For the next part of creating find max, well, really honestly, just use the find min and then go the, opposite direction. But again, we need to make sure that we understand that this is going to at first use some type of bootstrap in order to get things running, because in the code that you see in front of you here for just find min, let's say you just found that one, that's just not enough. So matter of fact, also find min, there's got to be another find min function, because here we have root, and the find min that you and I are currently looking at doesn't accept any parameters. So it has to be somewhere else. And that somewhere else is in the lower section, in the private section of this binary search tree.h. So further down in the file, here's the find min. So again, your find max should basically be the same idea, except for instead of left, it's going to be right. Now mine is slightly different in different ways, but either one will work. The one that you can copy and paste from find min or the one that I have will both work. The other interesting part is that now we're moving on to print tree, and print tree is supposed to print it out in infix order. A lot of the hints of what this function is going to look like is here in your find min and find max, where you're going to have to go in order. Means we process the left, then process, then go to the right. And a lot of the code's already here already. The other part is the overall setup is going to be exactly the same as find max, where we need a bootstrap and then the real function in order for it to do its job. So here is the print tree function, where we're going to display it to the screen, but the important part also is that number one, it checks to make sure that the tree is empty, and then number two, notice it calls a secondary print tree that's going to give it the root and how you want it displayed. So let's go to the real print tree function. And you'll notice, just like I said before, the order of the items inside here exactly like I said. We're going to go left, then print out the element, and then go ahead and go right. So all that's taken care of in print tree. Here's me using the print tree and the find max function. Two items of importance here is number one is that in the print tree itself, notice I don't have a cout. It took care of all that, and I'm going to show you it running here in a moment. And the find max, really, in either case, nothing's really super surprising. But what I wanted to show you was a mistake that I actually made, and that's the very, very bottom. Here I began to start deleting T3, which is my binary search tree. But remember that already in our deconstructor of the binary search tree, it takes care of all the memory deletion by the make empty function. So when I ran this the first time, I actually got a segment fault error because it was already deleted. Now when I run it, there's no surprises. Here it's displaying my new print in order method. It should print the numbers in ascending order and then the maximum value being 14 from that tree.